Today I will be discussing whether there is a function for the absolute percentage error in the period of a pendulum when using the standard formula. My team number is 60093. To model the simple pendulum, we consider a bulb of mass m attached to a rigid rod of length L. This bulb is pulled back at an angle alpha, measured from the vertical, and then released. There are a number of assumptions and simplifications that are made, as can be seen. The standard formula for the time period of a pendulum is well known. However, the crucial simplification that is made is that the angle of release is small. What happens though if we try to take into account the angle of release? In this case, we need a different model, which I shall call the actual model. Starting from the law of the conservation of energy, and using the fact that the pendulum may be considered as moving along the arc of a circle, we have the following expression for dt. Integrating this from alpha to 0, then multiplying it by 4, we have the time taken for the pendulum to complete one full oscillation. That is, we have an expression for the time period. Using trigonometric identities, then, we can simplify this expression. In order to try and evaluate this integral as simply as possible, we need to transform it into what is known as the complete elliptic integral of the first kind, defined as shown. To do this, we define a new variable phi, such that sine phi is equal to the sine of theta over 2, divided by the sine of alpha over 2. And note that as theta increases from 0 to alpha, phi increases from 0 to pi over 2. And after differentiating, we also have an expression for d theta d phi. Using this new variable, we can transform the integral so that we get the following expression for the time period. Comparing this with the complete elliptic integral of the first kind, we can see that the time period of the pendulum is equal to 4 times the square root of L over G, all multiplied by the complete elliptic integral of the first kind of k squared, where k is equal to sine of alpha over 2. We now wish to calculate t. To do this, we look at the general integral g of a and b considered by Gauss. Gauss was able to show that g satisfied the following identity. Now if we define a pair of sequences, an and bn, by the following recursion, it can be shown that these sequences converge to the same limit. And we denote this limit as the arithmetic geometric mean of a and b. Using this fact, as well as the earlier identity for g of a and b, if we take the limit as n tends to infinity, we find that g of a and b is equal to g of L and L, and this is easy to evaluate, and thus we have that g of a and b is equal to pi divided by 2L, where L is the arithmetic geometric mean of a and b. We can transform the complete elliptic integral of the first kind into g of a and b when we find that the complete elliptic integral of the first kind of n is equal to g of 1 and the square root of 1 minus n. So, using the formula for t found earlier, we can find that the time period of the pendulum is equal to 2 pi divided by the arithmetic geometric mean of 1 and the square root of 1 minus k squared, or multiplied by the square root of L over G. And note that an equivalent form for the arithmetic geometric mean of 1 and the square root of 1 minus k squared is simply the arithmetic geometric mean of 1 and the cosine of alpha over 2. If we compare the standard formula with the actual formula, we can see that the two are strikingly similar. In fact, the actual formula is basically the standard formula divided by the arithmetic geometric mean of 1 and the cosine of alpha over 2. If we now take L as being g over 60 meters for simplicity, we can plot the time period predicted by the actual formula shown in blue, against the time period predicted by the standard formula, shown in red. And clearly there's a discrepancy between the time period predicted by the two formulae, and this discrepancy increases as alpha increases. We now calculate the percentage error, and we find that the percentage error is equal to the absolute value of L minus 1 multiplied by 100%, where L is defined as the arithmetic geometric mean of 1 and the cosine of alpha over 2, as before. Note that we take the absolute value, since we are only interested in the magnitude of the percentage error rather than any sign. If we now graph the absolute percentage error against alpha, we see that the absolute percentage error increases as alpha increases. So let's start with the following result, and we now wish to find a function for the percentage error. However, no simple functional forms could be found, except one using the complete elliptic integral of the first kind, but then we are back to where we started. So instead, a statistical approach was used, where functional approximations for the percentage error were found. 5 regression types were compared by examining the R-squared value as well as plotting the graphs. The power model, y equals 0.0018 multiplied by alpha to the power of 2.0094, was found to be an excellent approximation for almost all values of alpha, as can be seen. The second model is due to Weisstein, who showed that the arithmetic geometric mean of 1 and b has the following power series. Note that this is only valid when b is small. Since the absolute percentage error is in terms of the arithmetic geometric mean of 1 and the cosine of alpha over 2, substituting b equals the cosine of alpha over 2, we have the following model, which I shall call model 2. If we now graph model 2 against the absolute percentage error, you can see that it is an excellent approximation for the absolute percentage error for larger values of alpha. Thus, we have two models which are good approximations for the absolute percentage error over different values of alpha. Thus, we can combine the two functions over different ranges of alpha to get the following approximation for the absolute percentage error. And this approximation only deviates by a maximum of 0.087 for all permissible values of alpha. So in conclusion, we have found the actual formula for the time period t, an expression for the absolute percentage error, and good functional approximations for the absolute percentage error in terms of two functions valid over different ranges of alpha. Finally, it is interesting to note that there are a number of further explorations that could be made in regards to time periods of pendulum. Thank you for listening to my presentation. And